All right, great. So last time we discussed left pulse vocalizations, and let's briefly recall what this is. The prototypical example would be you have a category of pre-sheaves on some site S, pre-sheaves of sets. Inside the category of pre-sheaves, you have the category of sheaves of sets, which includes include the category of pre-sheaves. And this inclusion has a left adjoint, which is known as the associated sheaf functor. This left adjoint sends some morphisms to isomorphisms. These are known as local isomorphisms. And so by the universal property of categories of fractions, the functor, the associated sheaf functor, factors through the localization functor that maps pre-sheaves to the category of fractions of pre-sheaves with respect to local isomorphisms. This factorization is a gashed arrow here. And one important result is that this gashed arrow is an equivalence of categories. The category of sheaves of sets is equivalent to the category of fractions of pre-sheaves with respect to local isomorphisms. And we would like to understand how this picture and how this description can be generalized to pre-sheaves of simplicial sets, now equipped with a relative category structure where the weak equivalences are the object-wise weak equivalences on pre-sheaves. And so the homotopy coherent picture would be a diagram of relative categories. And where on the left we previously had the category of pre-sheaves of sets and their natural transformations, now we have the relative category of simplicial pre-sheaves on S, their natural transformations, and as weak equivalences, we will take natural weak equivalences. Now, inside of this relative category, we can identify a relative subcategory of local objects, which we could also refer to as infinity sheaves or infinity one sheaves. They have the same morphisms and weak equivalences, and there is an inclusion functor. The inclusion functor has an adjoint, not in the usual strict one categorical sense, but maybe in some homotopy coherent sense, which is why I put this H here in the adjunction. And we expect that just like the associated sheaf functor factors through the category of fractions, there should be some analog of the category of fractions. And since weak equivalences are the maps we want to invert, universally, then inverting more maps, such as the local weak equivalences, which are precisely those natural transformations that are inverted by the associated sheaf functor, inverting local weak equivalences can be accomplished simply by enlarging the class of weak equivalences to local weak equivalences. So the role of the category of fractions is assumed by simplicial presheaves, natural transformations, and local weak equivalences as weak equivalences. And the associated sheaf functor, by definition, will factor because it sends all local weak equivalences to natural weak equivalences of the associated sheaves. And as it turns out, we can equip 2 out of 3 in this diagram. 2 out of 3 vertices in this diagram can be equipped with a model structure. The category simplicial presheaves per se can be equipped with a transfer model structure, also known as the projective. And the bottom right corner can be equipped with the so-called localized model structure, which is precisely what a left Balancic localization is, and that we will recall in a few minutes. On the other hand, local objects per se do not have a model structure because they are typically not closed under categorical, say, limits or co-limits in general. So this is just a relative category. This relative category will sit inside this model structure here, but it's not a model category. And to formalize what we to sort of express precisely what model structure we are using in the bottom right corner, that's exactly what left policy localizations do for you. And by the way, left here refers to the fact that the associated sheaf functor is a left adjoint. There's also much more rarely used right policy localization, which would be, say, for example, is how you construct a model structure on co-sheaves. For co-sheaves, you have the associated co-sheaf functor, which is a right adjoint, not a left adjoint. So a left Balancic localization in general would start with a model category C, such as simplicial presheaves with the projective model structure. So this would be a typical example of C. And it would take a class, a set of morphisms S. And unfortunately, S is a standard letter to use here. We have previously used S for a site. Now we are using it for something else. We are using it for the set of morphisms at which we want to localize. So a typical example would be check nerves of good open covers of Cartesian spaces. And you should think of these morphisms in S as some sort, they kind of generate this class of local isomorphisms. So every element in capital S will be some type of local isomorphism. On the other hand, there may be other local isomorphisms other than elements of S, because elements of S we assume to form a set, and local isomorphisms typically would form a proper class. And then we define an S local object as an object in the model category C, such that any element of capital S, any morphism S from A to B, sees X as a weak equivalence, in a sense that if you map A and B to X and look at the induced map between the simplicial mapping sets in the Hammock localization, you get a weak equivalence. And as it will turn out to be, in the case of interest to us, which is simply show pre-sheaves with check nerves of good open covers as elements of capital S, this definition will precisely recover the notion of a infinity sheaf among all simplicial pre-sheaves. And we'll explain more of this a bit later. And once we have defined local objects, we can define local morphisms. The definition is basically symmetric. A local morphism will be a morphism f from x to y, such that for any S local object A, once we map x and y to A, oh, and here I really should have put it in the opposite order. Oops. So once we map to capital A, we get a weak equivalence. This corresponds to the usual fact that in pre-sheaves of sets, local isomorphisms will be precisely those natural transformations, which once you map into some arbitrary sheaf, you get an isomorphism. So a completely analogous description can be given here. And RMAP, just to remind you, is another notation for the mapping simply shows set in the hammock localization. And previously we saw how this simply show mapping set up to a weak equivalence can be computed using co-Fibonacci and Fibonacci replacements. So somewhere here, I think. Yes, we explain how this mapping simply shows set up to a weak equivalence can be computed as if your model structure is a simplicial model structure, which it is in our case, then you will cofibonacci replace the source and Fibonacci replace the target. Then the enriched mapping simplicial set will be precisely the weakly equivalent to the mapping set in the hammock localization. So this is a very convenient way to compute derived mapping spaces. And so, for example, for the category of simplicial pre-sheaves, if you use this definition, then S local objects will be pre-sheaves satisfying infinity version or homotopy coherent version of descent, and S local morphisms will be local weak equivalences. And I would like now to use these definitions to formulate the universal property of left polycyclic localization, something along the lines of constructing a gashed arrow here. But in order to do that, we would need to first maybe say briefly a word or two about morphisms of model categories, or aka left equivalent functors. So we would like to we would like to formulate this universal property, which is sort of alluded to in this theorem, but first, let me say a few words about Quilling adjunctions. Yeah, so the basic definition is that of a left equivalent functor. Again, left refers to the fact it's a left adjoint functor. And this functor is also required to preserve cofibrations and acyclic cofibrations. And as it follows completely formally, every such functor has a right adjoint functor, which is known as a right equivalent functor naturally, and this functor will preserve fibrations and acyclic fibrations. So equivalent functors always common pairs, and that's why you also see sometimes the terminology like equivalent pair or equivalent adjunction being used in this context. And maybe one of the very first things to warn you about is that a left equivalent functor typically does not preserve weak equivalences, so it's not a morphism of relative categories. And sometimes it does, but usually, well, in like at least 70% of situations, it does not. Okay, but if it doesn't preserve weak equivalences, how exactly can we extract, so to say, an underlying functor of one of the models for infinity categories? For example, perhaps we want to extract an underlying relative functor or underlying functor of simplicial categories or quasi-categories. And maybe a nice observation about left equivalent functors is actually very easy to extract a relative functor, so it doesn't preserve weak equivalences, but a second very simple modification of it, namely if you precompose it with a confinement replacement functor Q, then the resulting composition, so first apply the confinement replacement and then the functor F, this composition does preserve weak equivalences. And the confinement replacement functor for us, we should think of it as something harmless, because if you may recall, every confinement replacement is equivalent to the original object via a natural transformation. So these morphisms depend functorial on X, which translates into a natural weak equivalence to the identity functor, which really shows like up to a weak equivalence. A confinement replacement can be replaced by the identity functor. So if you imagine morally here the identity functors, then you really see F back. So this composition of F with a confinement replacement is known as the left-derived functor of F, and is denoted by a bold capital L with F after it. And as it turns out, this is so the left-derived functor by definition, this is a relative functor. It preserves weak equivalences. And as it turns out, it will be in the appropriate homotopy coherent sense, it will be a left adjoint. And there are many ways to sort of formalize this. I only mentioned just one. This is a fairly recent result by Blomberg and Rio from about 10 years ago. If C and D are, let's say C and D are confinementally generated simplicial model categories, then the left-derived functor can be organized or lifted to an homotopy coherent junction of simplicial categories. More precisely, any left clone functor will restrict to a simplicial functor between bi-fibranch objects, and this restriction will be weakly equivalent to the original functor f, and it will fit into a homotopy coherent conjunction of simplicial categories. So in that respect, this construction here is a fully homotopy coherent construction. And why do I need to say this? Maybe I should have mentioned that there is a traditional definition somewhere here. I guess I should have mentioned. You will see a lot of such types of definition in the literature, so maybe I should say a remark, which is basically the traditional definition of a left-derived functor. So as before, you have a functor f, and in the traditional literature, you will see a definition such as D being a relative category maps to its homotopy category, which is simply the category of fractions in the traditional sense of D with respect to weak equivalences. And likewise, C also maps. And then the left-derived functor of f in the traditional literature, you can see it being defined as the left conic extension. So let me call this the localization functor of D. So this composition is the composition of LD and F. And we can then, if we have such a diagram, so two functors with the same domain, we can construct a left conic extension of this composition with respect to this localization morphism of C. The result will be a functor between the homotopy categories, so that's the traditional definition of LF. So this traditional definition is, as many definitions involving the homotopy category, is basically defective. Why is it defective? Well, it has so many problems. For example, the construction L, for example. Well, in addition to the fact that the result is a functor between homotopy categories, which means you already lost valuable information contained in C or D that is not present in the homotopy category, but this construction also has various other defects. For example, L does not preserve compositions. This is just one of many problems. So the traditional definition is defective what is a modern sort of solution to this problem? Maybe I should say modern definition. This was already observed in many works. I should probably cite Hinich. So since maybe some other people, sorry if I fail to mention somebody. And the fix to these defects would be simply to replace the homotopy categories with simplicial homotopy categories. Also known as the infinity localization. So, I mean, morally, this is just take weak equivalences and invert them up to homotopy. And of course, we saw one such realization of this idea, for example, Hammock localization. Well, of course, this is one of many. So, for example, you can also use the quasi-categorical constructions. They work equally fine here. And once you get this such a replacement, the traditional one categorical Khan extension should be replaced by its homotopy coherent analog. And as it turns out, this definition basically fixes all the problems that we identified previously. So first of all, it will no longer lose any information because it will no longer discard information by passing to the homotopy category, since a simplicial homotopy category actually retains all the valuable essential information. And
maybe a question.
Yeah.
So when you say this former definition of Khan extension is outdated, do you also include, like, I think this is, at least as I know it, the total left derived functor, and there is also this concept of just the left derived functor, where you like
Sure,
take
yeah, I mean, this is maybe, yeah, I mean, there are various flavors, so this is not maybe, yeah, you are correct, like usually the adjective total would
because
be prepended, yes. But
because I
the
think
other, I mean, yeah.
I just know that, so this is also used in, I think, Reel's book on categorical homotopy theory, if I'm not mistaken, but not with this, just with this definition, but also with, so you take this left derived functor, and then from this, you take basically the localization of this left derived functor, and then you end up with the total left derived functor and stuff like this. And the left derived thing is not given by a Khan extension, but the total left derived is given by a Khan extension. Would this, yeah.
Yeah, so as I said, yeah, the total left derived functor will be a Khan extension, yeah. Yeah, I mean, you can also say maybe something like there would also be like variants of this definition where you would land you would get a functor from the homotopy category to directly to D, for example. And this is of course again, it really depends on the definition you pick, but you can simply say yeah, I mean, one of such definitions can be found in Rio's book, but again, it will have the same problem and the same defects.
So
Because
just so I said, is the one I mean is like the left derived functor is really just a functor from C to D as well. So you don't pass through homotopy categories. at least.
Yeah, so if you use this definition, this is basically the modern definition. So if you just get a functor from C to D, then that's just one of the variants of the modern definition. In fact, in our case, since we deal with model categories, so for model categories, you can simply say or verify. This is actually a preposition. You can say that the left derived functor can be simply computed or is weakly equivalent to f composed with a confinement replacement. And you can generalize this construction a bit, where instead of model categories, C would be just a relative category. And then there's a notion of a deformable functor, which you can find in Rios' book, and also in the book of Dwyer, Hirschhorn, Kahn, and Smith. And the left deformable functor means a functor f between relative categories that need not preserve weak equivalences, but it admits a functor q from C to C, which is kind of like a confinement replacement functor. So q is naturally weakly equivalent to the identity functor, and f precomposed with q preserves weak equivalences. And you can prove that deformable functors between relative categories do have a do admit a left-derived functor in the homotopy coherent sense, and it can be computed using the same formula. So maybe the point of all of this is that this definition, either in its classical form or in its modern form, this Khan extension or its homotopy coherent Khan extension is difficult to compute in practice directly. And this formula gives you a very simple recipe to compute it in practice. So that's a very practical recipe, which, and notice this, of course, produces a functor from C to D. And this will be a relative functor. So, and you may ask, well, why, where exactly, what happened to the homotopy category, right? And here we kind of have a tautological observation that I mentioned many models for simplicial homotopy categories, such as hammock localizations or quasi-categorical localizations. But one such model is basically tautological, and maybe I should mention it, or the homotopy category of C, you can sort of model it as just the relative category C and its weak equivalences. So as one of the many equivalent models for infinity one categories, we have the relative categories, right? And in the language of relative categories, the notion of a simplicial homotopy category, or if you want the infinity one, so another sort of a modern name for this is homotopy infinity one category. So in the if you try to model homotopy infinity one categories using the language of relative categories, then basically it's a tautological construction. So the homotopy infinity one category of a relative category in this language can be taken to be the relative category itself, which is a kind of a tautological description, but it's perfectly fine to do. But do notice that For relative categories, morphisms are required to preserve weak equivalences. And this is exactly what is accomplished here. So here, this is this functor is a relative functor. It now preserves weak equivalences. And that's why it sort of, I somewhat, perhaps, if you want to be a bit more precise, you can say f comma q goes between the corresponding relative categories. This will be a more precise statement. It's a relative functor between the corresponding relative categories. Whereas here f is definitely just an ordinary functor. So here f is typically not a relative functor. So the left-derived functor construction, when expressed using the language of relative categories, turns a left equivalent functor, or more generally a left deformable functor, into an actual relative functor by precomposing it with capital Q. And you can prove that this construction satisfies the appropriate homotopy coherent expression of this notion of this modern definition. Okay.
Thank you.
More questions? Yeah, so this modern definition fixes the known problems. L now definitely preserves compositions, so that's fine. In fact, you can kind of tautologically seek for model categories. For model categories, once you apply Q, you are now inside cofibric objects, and left equivalent functors preserve cofibric objects, which means that composing functors, well, if the left-derived functor of a composition f and g will be just f, so gf composed with q, which is clearly the composition of derived functors. So the compositions are preserved, so everything works out very nicely. So once again, we see how getting rid of the homotopy category actually improves our situation. So that's a part of the general trend that the definitions given using homotopy categories can always typically be improved by passing to the homotopy coherent setting.
Please, may you reveal a bit more information about this reference with Shonemsky, Chisinski? Please, may you call the paper of this reference?
Probably the better source may be Sisinsky's book, Higher Categories and Homotopical Algebra. That's a book. It's available online. The PDF file is on his homepage. And chapter 7, yes. And Sisinsky has a Hinich has a paper which is called So what is a left-derived functor? And probably I should also mention, let's see, yeah, I think maybe the work of Mautsiniotis should also be mentioned here. Now that I think about it, Mautsiniotis also has a paper on in the spirit, a bit earlier paper. Yeah, but since this book is probably most accessible, yeah. Yeah, unfortunately, once you have the classical definition, you will be stuck with it for a long time before people very slowly switch to the modern correct. This is modern definition, I would really say, is the correct one. So but it will take time to switch. So the takeaway from this is that left-derived functor is how you extract, so to say, the actual functor from a left equivalent functor. So if you want to evaluate a left equivalent functor on some object, and this object is not cofibrant, then typically you would want to cofibrantly replace it first, and then apply the left equivalent functor. So that's pretty much the case always.
Please may discuss about intuition of notation related functor.
With which functor? Sorry.
Relative functor. Yeah. Intuition.
A relative
notation.
functor is just a functor that preserves weak equivalence. So basically, the only intuition we should keep in mind here is that maybe I should have relative categories and relative functors. Are one of many equivalent models for infinity one categories. These are just functors that preserve weak equivalences, and for example, an equivalent model is simplicial categories and simplicial functors. So categories enriched in simplicial sets and functors that are enriched functors. So say here the equivalence is given by the hammock localization. Another useful model is quasi-categories. Here there is a sort of functor which sends a relative category CW to the homotopy coherent localization. Let me put H to say it's homotopy coherent or quasi-categorical localization, and not just the usual category of fractions. Yeah, and there are other equivalent models, but the point is that all those descriptions are equivalent, so relative functor is precisely what you need to get one of the equivalent models for infinity one categories. So all of these guys model infinity one categories. And later we'll see even more models such as Siegel categories, complete Siegel spaces, and so on. So that's the intuition behind a relative functor is just what makes this construction work? All right. Any more questions about derived functors or left equivalent functors or anything along those lines?
As I understand, that related functors, they are one of the ways, 7 ways, as I remember, for constructing quasi-categories. Yes, as I understand.
Functors of quasi-categories, yes. So of course, this construction is a functorial construction. So if you have a relative functor to some other category D, WD, then of course you have an induced functor of quasi-categories. And of course, the reason you do have such an induced functor is precisely because the original functor preserves weak equivalences, so it sends elements of W to elements of WD. And if this wasn't the case, then you wouldn't be able to define this induced functor, because this functor, of course, is defined using the universal property of localizations. And in order to define the induced functor, the morphisms you invert here must be sent to invertible morphisms here.
Thank you.
Yeah. All right. So now that we know what a left equivalent functor is and what a derived functor is, we can finally formulate a universal property of left Gauss localizations. So let's say I have some C, a left a model category, and S, a set of morphisms in C. S is given by some model category denoted LSC, and a left equivalent functor L, the localization functor. And in this case, this functor actually will preserve all weak equivalences for the very simple reason that cofibrations will be preserved, so and cofibrant objects will be preserved. So all right, so and what is the universal property of this functor? Well, it's formulated in 2 parts. The first part says the left-derived functor of the localization functor sends elements of capital S to weak equivalences. So the left-derived functor of the localization functor capital L inverts all elements of capital S in the sense of turning them into weak equivalences. And the second part of the universal property says if you have another functor, f is another left equivalent functor with the same property that the left-derived functor of f turns elements of S into weak equivalences, this time in D, then there is a unique functor G the gashed arrow here, which is a left equivalent functor, so maybe I should say and here, of course, f is also a left equivalent functor. And the composition of L and G has to be equal to F. So this triangle has to commute. And if you are watching carefully, watching things carefully, you may see that somehow this definition appears to be more strict than it should be. For example, I'm saying G is unique not up to a unique isomorphism, but it is actually unique in the strict sense. And this is by design because the stronger property, of course, the strict property will imply the not so strict property, and but the strict version allows us to sort of fix a specific model for the left Pavlov localization. So in fact, the underlying category of C and its left Pavlov localization will be exactly the same category. And cofibrations in true model categories will also be the same. And so the only thing that differs between the true model categories will be the weak equivalences. So weak equivalences of the left Pavlov localization will be precisely the S-local weak equivalences that we defined previously. Where exactly have we defined them? Oh yes, right here. Well, probably I should say S-local morphisms because they only become weak equivalences once we form a model category out of them.
Quick question, maybe.
Yeah.
So this definition of left Pavlov localization, so it should basically be so if we view model categories as infinity categories, then this should be an infinity categorical reflective localization in some sense, right?
Yes,
So
yes, that's
is this
exactly
the
right. So maybe we should mention a connection, yes, to let's see. So somewhere here, maybe we should say yeah, as an observation or remark or proposition, maybe even probably should be attributed to Szyszynski also. In his higher categories and homotopical algebra book, you can find proof. And one way to formulate this proposition is to say that if I have my left Pavlov localization, this will be a functor, a left equivalent functor. In fact, it preserves weak equivalences. So there is no need to derive it because the derived functor will be weakly equivalent to the original functor. So we can take L as its own derived functor, and L, of course, induces a functor of quasi-categories. So suppose C and S are is a model category in a set of morphisms. Then you have an induced functor of quasi-categorical localizations. Which I'm also going to denote by L. And here I invert the weak equivalences in the left ballistic localization, which are precisely the S-local morphisms. And in quasi-categories, this localization functor now has a left adjoint, sorry, a right adjoint, So this is a right adjoint in the quasi-categorical sense. Let me put H here to again remind you it's a homotopy coherent notion. And so it's a quasi-categorical right adjoint, and this functor is fully faithful. Fully faithful in the sense of quasi-categories, meaning, well, one way to say it is it induces on a weak equivalence on all mapping simplicial sets. And this is the usual quasi-categorical definition that you have a full subcategory and the inclusion functor has a left adjoint. So that's what is known as a reflective localization of infinity one categories.
That's very nice, thank you.
Yeah. All right. Yeah. And let me finish the review of left ballistic localizations by saying that the existence result, which I'm not going to prove, it's a small object argument basically, but the left ballistic localization exists if S is a set of morphisms as opposed to a proper class. The underlying category of C is locally presentable. C is cofinitely generated as a model category. Let's recall that this means there is a set of cofibrations as opposed to a proper class that generates all cofibrations or generates all acyclic vibrations via the right lifting property. And finally, C is required to be left proper. Left proper means if you have a maybe I should have said this somewhere. I ran out of space, but left proper means if you have a commutative square, if you have a push-out square in a model category, and one of the maps is a cofibration and the other map is a weak equivalence, and then you can conclude that the map opposite of the weak equivalence is also going to be a weak equivalence. So that's what left proper means. Under those conditions, which turn out to be very mild, I mean, the first three are basically tautological and trivial to verify in practice. Left properness is not always satisfied, but it is true in pretty much any practical example we are interested in. In particular, it is true for simplicial presheaves, because for simplicial presheaves, any projective cofibration is degree-wise or object-wise cofibration, and which reduces the verification of this property to simplicial sets. And for simplicial sets, it's true because, well, push-outs along monomorphisms do preserve weak equivalences, yeah. All right. So now let's move on to our main example, which is the Czech local model structure. This one, of course, models infinity-long sheaves. And here I formulated everything for the site of Cartesian spaces. But of course, it could be replaced by any other site. The only change you would have to make is, in general, intersections of open subsets would have to be replaced with fiber products. But we are mostly interested in the site of Cartesian spaces, so let me sort of, for simplicity, concentrate on this example. So my model category C is going to be the category of simplicial presheaves equipped with the projective model structure, say. Let's recall that projective means that weak equivalences and fibrations in this model structure are defined object-wise. So a natural transformation is a weak equivalence or a fibration if all of its components are weak equivalences or fibrations of simplicial sets. And the set of morphisms S will be the set of will consist of Czech nerves of good open covers. And previously, maybe 4 or 5 lectures ago, we saw how the Czech nerve construction works for presheaves of groupoids. Now we will replicate this for simplicial sets, and it will be more general for that reason. Let me introduce, so let's start with some good open cover of a Cartesian space X. Let me introduce a notation for intersections of elements of this open cover. So U with a multi-index I, here, I is a multi-index, is defined as the intersection of all U's indexed by elements of I. And this intersection for a good open cover is required to be either empty or a Cartesian space itself, meaning it's diffeomorphic to a Cartesian space. And UI is required to be also isomorphic to a Cartesian space. So now the Czech nerve of U will be a morphism of simplicial presheaves from certain simplicial presheaves that we construct right now to the representable presheaf of X. So Y is a Onega embedding here. So that's what I recall here. So what is a Czech nerve? In simplicial degree N, I'm going to take a disjoint union or coproduct over all multi-indices I with n plus 1 elements. Notice here I is indexed from 0 to n. That means n plus 1, you have n plus 1 elements corresponding to the n plus 1 vertices of an n simplex. And I can only check those UIs for which the intersection is non-empty, because and the reason for that is that, well, the empty set doesn't really contribute anything, but also the empty set is not an object in the Cartesian site. So in order to make sense of this unique embedding, I must have a non-empty object anyway. So I take such a huge disjoint union. And the structure of a simplicial object. So this is just the object of n simplices, which is a pre-sheaf of sets. And now all these individual pre-sheaves of sets can be organized into a simplicial object by declaring that the case face map, for example, will be a map from C un, check un, to check un minus 1. How does it work? Well, let's recall that both sides are a disjoint union of certain representable pre-sheaves of certain intersections, indexed by some multi-indices I and j of lengths n plus 1 and n respectively. And to define a morphism out of such a coproduct, I might as well define it separately on every UI, which is the representable pre-sheaf of the intersection. And what the case face map, sorry, it should be really dk here. What the case face map does for you is simply removes the case factor from the intersection. So uik is removed from the intersection, and you have you rank in the intersection of all the other UIs. So this will be an intersection of n objects here. So we will rank inside the previous step of the construction. So a face map simply removes the corresponding factor. And the degeneracy map will, as you can guess, is going to duplicate the case factor. So if you can duplicate an element in the intersection, and adding one more identical term is not going to change the intersection. So just to give you an example, maybe if you have an open cover with two elements, I'm going to see the disjoint union of v, say, two elements v and w. Then I'm going to see the disjoint union of representable pre-sheaves of v and w in degree 0. And in degree 1, I'm going to see a disjoint union of 4 terms. The first two will be simply the degeneration of the zero simplices. And there will be two more corresponding to the other two possible intersections, v and w and v. And if you follow the discussion, the previous discussion on descent for sheaves of groupoids, you may recall that there we perhaps use something a bit differently. We were basically interested in what we can now identify as the homotopy pushout. So v and w, we can take the pushout along the intersection. But as it turns out, there is a canonical map to the Czech nerve, and this map is a weak equivalence. Basically, what is happening here is, although you may see like two different copies of the intersection in the sheaf of one simplices, it turns out that these two copies are going to be made weakly equivalent by true simplices. So there will be a true simplex which makes this part, this intersection, weakly equivalent to this intersection. So even though it may look like we have more than just the intersection, we somehow have two copies, but these two copies will be made weakly equivalent to each other. Oh, and of course I should have mentioned I not only want the simplicial p-sheaf, but I also want this map to the representable p-sheaf of X. But this map is sort of tautological because, of course, every intersection, every UI embeds into X via the canonical inclusion. So what is going to happen now is we are going to take these maps from the Czech nerve to, yeah, I should have said this a bit more explicitly. So we are going to take these maps from the Czech nerve to the representable p-sheaf of X, and we'll take them as our set S. So what's going to happen is we are going to pick an arbitrary simplicial p-sheaf F, and we'll start mapping the domain and codomain of this map into F. So this will induce a map on derived mapping spaces. So the derived mapping space from the representable p-sheaf of X into F. This will map to the derived mapping space from the Czech nerve of the open cover to F via the restriction along this map here. What is nice about the projective model structure is that the both derived mapping spaces can actually be computed as ordinary mapping spaces. So for the left side, we know this pre-sheaf is representable, and representable pre-sheaves are cofibrant in the projective model structure. Essentially, that's the case by definition, or I mean, you can clearly see that this pre-sheaf has a appropriate lifting property with respect to all projective acyclic fibrations, because projective acyclic fibrations are object-wise acyclic fibrations, and these are clearly going to have a lifting property with respect to a representable. But also the Czech nerve turns out to be cofibrant. And the reason for this is previously we discussed how a criterion for cofibrancy of in the projective model structure turns out that being cofibrant in the projective model structure, let me recall the criterion that we did mention briefly at least. Yeah, so here we have a cofibrant criterion for cofibrations, right? Or cofibrant objects, and we said an object, a simplicial presheaf T, is cofibrant if for any n, the object or the presheaf of sets of n simplices splits as a coproduct of degenerate n simplices and some other presheaf. You can already see this happening already in this example. This part is degenerate and it splits off as a coproduct, right? The leftover is this presheaf here. They split as a coproduct. And the second condition was that the remaining part is T and hat. So what you get after you remove the degenerate simplices, the remaining part splits off as a coproduct of retracts of representables. And that's exactly what happens here. You have a coproduct, and individual summons will be representable. So that's clearly satisfies the criterion. This picture will persist in higher dimensions. Yeah, so the derived mapping spaces can be computed as the ordinary mapping spaces, ordinary simplicial mapping sets, and by the enriched Jungian lemma, the derived mapping simplicial set from the representable presheaf to F is simply going to be the same as the evaluation of F at X. So this is a simplicial set. This morphism is a map of simplicial sets. And the way you think about this morphism, this what I denoted by green Z here, is this morphism is the analog of the what we previously wrote several lectures ago of the restriction map from f of x sections over x to the set of all what we at that time called compatible families, or input Geka for the gluing construction. And one way to explain what an infinity one sheaf is to say this morphism D is a weak equivalence for any good open cover U. So the restriction map from sections from the simplicial set of sections over X to the simplicial set of compatible families. So this is just the simplicial set of compatible families. This map is a weak equivalence, and Mao is saying that F is an infinity one sheaf. So you can see the definition, in fact, pretty much resembles the usual definition, except that we were slightly more sophisticated when we defined what a compatible family is. But otherwise, it's basically a precise replica of the usual definition. And an observation we can immediately make here is that this condition of being an infinity one sheaf is, of course, a locality condition in the sense of left Bowles localizations. So let's again look at this definition here, right? So an S local object was defined as an object X such that mapping any morphism in S into it produces a weak equivalence. And morphisms in the hammock localization, these are just derived mapping spaces. So we see that the locality condition for the maps from the Czech nerves to the object they cover is precisely the infinity-1 sheaf condition, right? So the locality condition would read R map from Yx to F to R map from the Czech nerve to F is a weak equivalence. So this immediately leads us to the definition of the Czech local model structure on simplicial presheaves on Cartesian spaces as the left Bowles-Field localization of the projective, I should have said is the projective model structure taken here. And you left Bowles-Field localize it with respect to the set of morphisms S, given by the map from the Czech nerve to the corresponding representable object. And the existence of such a model structure again follows from this theorem of Smith's that I already briefly mentioned. Where exactly is it here? Yeah, briefly mentioned here. This was the original application of the notion of a combinatorial model category. So, and weak equivalences in this model structure are known as local weak equivalences or Czech local weak equivalences. And in the case of the Cartesian site, and let me emphasize that this description is only true for sites with enough points, like the Cartesian site. So that will also be the Skok-wise weak equivalence. So in the case of the Cartesian site, we can say a morphism of simplicial presheaves is a weak equivalence if for any n greater than or equal to 0, the induced map on Skoks. So Skoks will be simply co-limits of simplicial sets given by evaluating f on an n-dimensional ball of open ball of radius epsilon, where epsilon gets smaller and smaller, and you take the co-limit as epsilon approaches 0, and this resulting map will be the induced morphism between Skoks, and this map has to be a weak equivalence. Cofibrations will be precisely projective cofibrations. As I previously mentioned, cofibrations don't change under Bowles-Field localizations, left Bowles-Field localizations. And finally, fibrant objects will be precisely those objects that are both fibrant in the original model structure. So fibrancy in the projective model structure means you are object-wise fibrant, which in our case boils down to being a presheaf of Kahn complexes. And you also must be a local object, which means you are an infinity-1 sheaf in the sense we talked about here. So this map has to be a weak equivalence. Sorry, not this map D. So this is the infinity one sheaf condition. Okay, so I hope this gives you some intuition what the Czech local model structure is. Any questions before we consider some simple examples? All right, so let me finish for today by considering this very simple example of a de-looping of a Lie group. So let's say G is a Lie group. You take your favorite Lie group, like, I don't know, invertible matrices or complex numbers of absolute value 1. And its de-looping BG will be a simplicial pre-sheaf on the set of Cartesian spaces. And notice here I'm using a bold B to distinguish de-looping of simplicial pre-sheaves from de-looping in the usual sense, which is what is used here. So the resulting simplicial pre-sheaf, BG, so simplicial pre-sheaf on the Cartesian side, and it sends a Cartesian space U to the simplicial set given by the de-looping of a group, which is simply the group of smooth maps from U to G, equipped with a pointwise multiplication. So this is a group, and for any group or for any discrete group, we can take as de-looping. Its de-looping will be the nerve of a groupoid with a single object whose endomorphisms are precisely this group that I have here. So that's what I assign to a Cartesian space U. As you can see here, basically I have the representable pre-sheaf of G, which justifies this notation. So strictly speaking, I should have written bold B of the omega G. So bold B applied to the representable pre-sheaf of G, which will be a pre-sheaf of groups. Okay, so here are some observations about this resulting simplicial pre-sheaf BG. It will be a fibrant. It will be a fibrant simplicial pre-sheaf, meaning it is a pre-sheaf of Kahn complexes because nerves of groupoids, such as this groupoid here, are automatically Kahn complexes. In fact, there's a characterization of groupoids among all categories. So the nerve of a category is a Kahn complex if and only if the category is a groupoid. And secondly, this pre-sheaf BG satisfies descent, which is a non-trivial fact. And let me illustrate it for good open covers consisting of two elements, V and W. So VW is a good open cover of X. So their union is X and their intersection is a Cartesian space. Then the descent morphism will be a morphism from BG evaluated on X. True. And on the right side, I will need to put this mapping simplicial set from the Czech nerve to F. And in this example, let me cheat just a tiny bit. And previously, I observed that the Czech nerve for open covers with two elements, the Czech nerve is equivalent to the homotopy push-out. And derived mapping simplicial set out of the homotopy push-out can be computed using a universal property, which basically means you can replace it with a homotopy pullback. So this is just a homotopy pullback. Homotopy pullback of a diagram where you map individual terms in the homotopy pushout to the simplicial presheaf BG, and mapping a representable, like here, representable of V, representable of W, simply amounts to evaluating BG on V or W or their intersection. And now we can see that the right side can be described much more explicitly. So we have a homotopy pullback of simplicial sets given by nerves of groupoids. And the nerve functor commutes past homotopy pullbacks. So you might as well say that this right side can be computed as a nerve of the groupoid given by the homotopy pullback of groupoids involved in the construction of these three simplicial sets. So what is this groupoid on the right side? An object in the homotopy pullback of groupoids will be an object here, and an isomorphism between their images here. But these two groupoids have a single object by construction, right? So there is a single object here, a single object here. So the gauge of an object in both factors will be redundant. And the only thing that will survive will be an isomorphism between their images here. In other words, the geika of an object in the homotopy pullback will be precisely the geika of an isomorphism in this groupoid here. This is just a smooth map T from the intersection to G. And what is a morphism? A morphism in the homotopy pullback of groupoids. Well, if you have two objects, true objects T1 and T2, then a morphism from T1 to T2 will be, well, it will be given by a morphism in this groupoid, a morphism in this groupoid, and when you send both of those morphisms to the intersection, a second compatibility condition must be satisfied, which is expressed precisely by this equality here. Okay, so how do we think about this homotopy pullback? This homotopy pullback expresses precisely the co-cycle Geiger for principal G bundles. Trivialized over the open cover VW. If you recall, to specify a principal G bundle using a co-cycle Geiger amounts to specifying an open cover, and for any pairwise intersection of elements in this open cover, you have to specify a transition function, which is what we call T here, and that's why the letter T was chosen. Is the transition T is for transition function. So this T is just a transition function. And strictly speaking, these transition functions must satisfy a co-cycle condition, which in our case is trivial because the co-cycle condition is formulated for triple intersections. And in our case, the only triple intersections will be degenerate. So the descent object in this case precisely recovers the description of principal G bundles in terms of co-cycles. But now, to show that this map here is of weak equivalence, it is enough to observe that there is no difference in description of principal G bundles as just so the left side is a groupoid with a single object and morphisms as indicated here. Smooth functions from X to G. This is just a groupoid of principal or trivial principal G bundles over X. Now, let's recall that X is a Cartesian space. A Cartesian space is contractible, and over a contractible space, every principal G bundle is trivial. So there's no difference between trivial principal G bundles and arbitrary principal G bundles over a Cartesian space. And this in this groupoid, the only object, you should think of this only object as the trivial principal G bundle. And this group is precisely the group of automorphisms of the trivial principal G bundle. Such an automorphism is given by acting on the fiber over any point of capital U by some element of G. So this restriction map is simply sends a trivial principal, the groupoid of principal G bundles over X to the groupoid of co-cycle Geiger of principal G bundles trivialized over the open cover V and W. And of course, you can see that we are going to get an equivalence of groupoids here because essentially the true descriptions are the same. So both left side and right side describe principal G bundles over X. The left side, strictly speaking, is trivial principal G bundles over X, but X is contractible, so every principal G bundle is trivial. And the right side describes principal bundles, or rather their co-cycle Geika, trivialized over the open cover V and W. But again, any such Geika glues to a principal G bundle over X, and conversely, every principal G bundle does trivialize over a glued open cover, because V and W and V intersect W are all contractible spaces. So indeed, we do have an equivalence of categories. That's what I sort of indicated here. So this is an example of a fibrant simplicial pre-sheaf in the Czech local model structure. And I think that's a good time to stop for today and see if you guys have any questions left. All right, if there are no more questions, then I guess I'll see you guys next Sunday. Oh, and if any of you want to talk about the homework problems, by all means, feel free to do so. I'm happy to discuss it on Zoom, or if you prefer, on the Discord server. I think Alex and Jacek are already done, I think, the first 3 problems or so, right? And or at least make a lot of progress on the first 3 problems. So in fact, I think everybody else is also welcome to join them in the discussion. So
Thank you for the lecture.
all right, then that's it for today, and I'll see you next week.
Thanks for the
Bye.
lecture.
Bye.
Bye-bye.